Welcome to this presentation on Z transform theorems. In this brief video, we will discuss the properties of linearity, shifting and convolution. We will take up linearity property first. Given the following Z transform pairs, that is the sequence U1 of n has a Z transform U1 of Z, U2 of n has a Z transform U2 of Z, the following relation with arbitrary alpha and beta holds. Z transform of linear combination of U1 and U2 give rise to the same linear combination of the Z transforms of the individual sequences. Here the symbol with two arrowheads relates a pair, it relates a time domain signal with its Z transform. We will use this symbol frequently in this course. We will take an example, find the Z transform of U1 of n, which is given as the difference between two impulse sequences. Remember, although I have not put the braces here, it is understood that each one is of infinite duration. Of course, some simplifications are possible because of the nature, namely that this is delta of n. So let us take U1 of z by definition, this whole thing multiplied by z power minus n going from minus infinity to plus infinity. Similarly for the second term, 3 comes out of the sum, once again you have this infinite sum. But as delta is something special, we have some simplifications. What is special about it? This delta is non-zero at only one point for only one value of n. At what value of n? When n is equal to 0. When n is equal to 0, this becomes 1, this becomes z to the power 0 and hence this becomes 1. So I get 1 for this entire infinite sum. Similarly, this becomes 1 when n is equal to 2, so I have to put z to the power minus 2. For all other terms, this sum is 0. For all other n values, the elements in this summation become 0. So we do not have to consider those. Only thing we have to make sure is that z inverse is finite, so this whole thing is finite. Remember, we are choosing z such that this entire z transform is bounded. So this linearity rule is useful to evaluate z transform of sum of sequences. We will come across such sequences frequently in this course. Next we will take up the z transform of shifting. So u of n plus d is u of n plus d times z to the power minus n. What happens in this case? So I write as z power d outside and multiply again by z power minus d, take that inside, so it becomes z to the power minus of n plus d. And what is this sum? You see that this is nothing but u of z. You can just substitute n plus d as m, so u of m into z power minus m going from minus infinity to plus infinity, because this d is finite. So we obtain z power d into u of z. So for all finite d, this equation is satisfied. This u of z is the z transform of u of n. So let us see some examples. If un is u of z, then u of n plus 3 is z to the power u of z. Previously we had d here, we got d here, now the d is 3. The next example we have minus 2, so we have minus 2 here. What happens in the case of minus 1? We will have minus 1. This pair is something special because it defines the delay element. Z power minus 1 is known as the delay element because it shifts the signal back by 1. So, u of z would have given u of n, you multiply by z power minus 1 and you invert it, you get u of n minus 1. So, this is known as the delay element z power minus 1. This is going to be extremely useful in direct realization of Z transforms, which we will see shortly. One gets a slightly different result if one-sided Z transform is used. But of course, as mentioned earlier, we will have consistent results as per our definition. We will next take up the Z transform of convolution. Suppose we have two sequences un and gn with their corresponding Z transform uz and gz. Then the convolution of these two will have the Z transform gz into u of z. Here you have to just multiply. On the left hand side you are taking convolution, on the right hand side you are only multiplying. Why is it? Recall the motivation slide for Z transform. In fact, it is to do this we defined Z transform. Instead of carrying out convolution, we just multiply, because that is how Z transform is defined. That is the beauty of Z transform. Recall that the symbol asterisk denotes convolution. This is of course proved in the textbook formally. I want to give an example of Z transform of convolution. Let us calculate the step response of a system whose impulse response is given by this g of n, which is nothing but 0.5 to the power n into 1 of n. Recall that 1 of n means unit step signal. We want to do this using Z transforms. Previously we calculated the same thing through convolution. So let us evaluate g of z. So what we will do is we will evaluate g of z, we will calculate the Z transform of the step, we will multiply that 2 and then we will obtain the result. So let us evaluate g of z given g of n to be this. Okay, this is the way we defined Z transform. Let us substitute. Now because you have unit step which becomes non-zero from n equals 0 onwards, I start from 0. For all negative values this term is 0. From j equals 0 onwards the value of 1 of n is 1, so I do not have to put 1. So I get only 0.5 to the power j and I write this z power minus j here. So let us evaluate this sum. So let us substitute for j equals 0, it is 1, for j equals 1 it is 0.5 z power minus 1, for j equals 2 0.5 z power minus 1 whole to the power 2 and so on. Okay. Now we can write this infinite sum as follows. This is the geometric progression. Remember, in order to do this we have a condition that each of these terms is less than 1. In other words, this absolute value of z should be greater than 0.5. Only under this condition can we evaluate this sum and represent it as a compact ratio like this. Okay, this is for g of z. What about input? Input in this case is a step. So let us evaluate this. Using this formula we will take our u to be the input. Let us take the Z transform. Now once again u of j is nothing but 1 of n or 1 of j. So j equals 0 onwards it starts, goes up to infinity and we do not have to put 1. So you have z power minus j. And using the same approach as earlier, you see that this becomes equal to 1 over 1 minus z inverse. So we assume that each of these terms is less than 1. In other words, z is greater than 1. Absolute value of z is greater than 1. Let us recall how do we find the step response. Step response of this system means step is given as the input then we have to convolve this with g of n to get the output. So in other words, output y of n is equal to g of n convolved with u of n. In terms of z transform, we just have to multiply g of z and u of z. This is because of the convolution property that we saw in the previous slide. So we multiply the z transform of g with that of u. So this was the z transform of g, this is the z transform of u. So let us multiply these two, and we have taken z to be greater than 1. We wanted this to be such that absolute z greater than 0.5, region of convergence for this. For this, the region of convergence is greater than 1, z greater than 1. So we have taken the larger of this, namely absolute z is greater than 1, that will satisfy the condition for this also. So it is easy to check that this above expression is equivalent to this. So at this point I am not explaining how I obtained this, you can verify easily. The denominator is the same. I want you to just simplify this, take this as the common factor, cross multiply, simplify, you will get this. On inverting this expression, we obtain this is the z transform, this is 2 into 1 power n minus this is 0.5 to the power n into 1 of n. This comes from the very definition of z transform. When I simplify this, it becomes 2 minus 0.5 to the power n into 1 of n. This is identical to the expression derived earlier. We derived the same expression when we were dealing with convolution in the discrete time sequence video. Of course, recall the motivation that we explained to define the z transform. With this, we come to the end of this presentation. Thanks for joining.